So we are going to see how the reaction modeler works here, and the scale that we can use, or the type of the simulations that we can do here is either full atomistic model or united atom model, or we can again, like, once these two scales can be utilized for configuring the reactions and doing the reactions. And as you can see, we have the manual as well as the two tutorial files are available here, and we are going to try one of these tutorial here to explore all the options available under the reaction modeler. So the first option, or you can say the tutorial, which is about the chain reaction, and the second tutorial talks about the two-step reactions. So we are going to first see how this chain reaction works, the first case that we are going to simulate here. So before to start with the reaction modeler, we have to create some input files. Since this is a chain reaction, so we should in the chain reaction we should be having the initiator as well as the reactant. So to simulate or to showcase this particular reaction modeling, we are going to create the input initiator and the reactant. To create that, we are going to use the monomer modeler for the generation of the initial initiator and the reactor. Okay, so this is the directory that I have created here, and if you right click on it, then new monomer, and again the new file. Okay, so I'm going to name the initiator as ch3 as the name itself. So this is the initiator, and as you can see, now we are going to draw, as you might have seen in one of the previous slides, how we do the creation of the model. So we have selected the carbon atom and the chosen the bond, single bond. So we are going to just drag and drop, and it's going to create a model for us. Okay, and hydrogens will be automatically selected, but I can if you want to visualize, so this is how we can draw them. And chlorine is also required, so I chose the chlorine. And since this is an initiator, we are going to leave one position available for the reaction to start with. So for that case, we are going to add no hydrogen options available, because if we don't add this particular no hydrogen options, this is our system will add hydrogen automatically at this particular position to satisfy the valency of this particular carbon. To avoid that, we have to use this no hydrogen, or in the under the cap direct cap tab cap. So this is how we have created, and next is again we'll follow the same procedure. We are going to apply the force field, and one more thing we have to keep in mind, that we have to stick to one particular force field throughout the simulation of the reactions to maintain the consistency in the force field. So once we have applied the force field trading, and we have to do the molecular mechanics calculation to obtain the spatial coordinates for our initiator. So once we start with the default conditions, as you can see, we have our spatial coordinates of the initiator. And as you can see, the hydrogen is not been added since we instructed the system not to add one. So this is how our initiator molecule looks like. The next is doing the molecular orbital calculations. Again, we have multiple options of doing that. So for this particular case, we'll use the default Mosemi option to do the or calculate the charges. As you can see, it has calculated, and this is some extra excess charges available. We can just set it to 0. Once this is done, then we are good with our initiator. The next is to creation of the reactant. Again, we'll follow the same method. So it will be named as CH2, CH, and Cl. It's up to you. You can name it whatever suits for you, or whichever you're comfortable with. So right now I'm just creating and even following the tutorial PDF. Okay, so I've chosen the carbon and the type of the bond, double bond. So this is how we can create it. Next again single bond, and let's add the remaining hydrogen atoms for the valency of the carbon, and the chlorine again, and one hydrogen atom here to satisfy the valency of this particular carbon. Once this is done, we can go on to choose the force field that should be applied here, followed by the molecular mechanics calculations. Once this is done, close it, and then you'll be able to visualize. And then we'll do the molecular orbital calculation to find out the excess charges. If it is available, it is not, we'll set it. So these were the initials, or you can say the prerequisites to start with the reaction modeler here itself. Is we have to create our reaction modeler file. So we have to choose the reaction modeler either from there, or you can directly choose from here, and it will pop up into the current working directory, and we can name it, since this is going to be the chain reaction. So I am naming it as chain reaction, and you'll see the extension of this input file is .rcn. So here we are going to add the monomers, and to add the monomers which is required for the chain reaction modeling, we have to use this option of register monomer. Suppose if you want to delete a particular monomer that you have added, that can be done with the delete monomer. Next is, if you want to register a polymer as well, you want to utilize previously configured or the generated polymers to be utilized for the chain reactions, that you can add from these options available here. The other options which are available here for the chain reactions, I will explain each and every options which are available here for the coming reaction options. The first thing that we are going to do is to choose the monomer. So we'll add from there, click OK, and as you can see, we have added our first monomer. Similarly, we can add the second monomer as well. Okay, so we have added our both the monomers for the reactions to take place. Now in this particular situation, a special condition is to be met. Since we have added a no hydrogen particle here, we have to give a special condition. That condition you can find under these options of special settings, and here it says allows the scission of no hydrogen bonding reaction conditions and allow the same reaction numbers for different monomer. Okay, if I don't check these options available here, the reaction point which I am going to choose won't allow for the next monomer to be used. As you can see, these two options are not available for the another monomer which is available here. To allow such options to be used there, we have to check these options as well, which says allow the same reaction numbers for the different monomers. Once we check these two options, then it will be able to give you the options to choose the same reaction sites for different monomers which is being utilized in this particular chain reactions. So now for this particular case, we are going to rename this reaction point 1 in both the different monomers here. The reason being, these two sites are similar quite, and what we are going to do is we are going to break this particular bond, and after breaking this bond, we are going to make a bond with at this reactions point 2, and similarly it is going to follow for the next bonding process in the chain reactions, as this is our the initiator which will initiate the chain reactions, and this is the reactant. So we have assigned the reactive sites where reaction is going to take place. Next is to assign the symmetry points, and these symmetry points are to tell the system that these are the symmetrical points in the monomers to uh, save some computation power. So for that case, we can use these symmetrical points. So since, as you can see, for this one particular carbon atom, these hydrogen atoms are symmetrical, so I am going to name it as 111. So if either my system has to calculate for this one hydrogen atom, and it will give all the values similar to the this other hydrogens. So once we have assigned this hydrogen atom for this initiator, similarly we can give the symmetry points for the others as well. So this is something different than these hydrogens. And then the chlorine, they are given the symmetry points and the reactive points for the initiator. Similarly, we are going to give the same conditions for here for the reactant as well. So these hydrogens are similar, whereas the others are not. So we'll follow the similar conditions to give the symmetry points. Now we have given the initial conditions that to be met, the reaction sites and the symmetry points. The next option which is available here is the setting the reaction condition. I explained already that we are going to break this bond of 1 and 3 and going to connect with the initiator monomer. So to add the reactive conditions, we have to use this option of add condition, and then it will add up. We are going, as this chain reaction is going to take place under one group, so whatever the chain reaction conditions that I am going to provide will be this under same group. If you have reactions where in the next tutorial where the two-step reactions are going to take place, two different groups will be assigned for the reaction conditions. The first thing is that we are going to break this bond between the reactive points 1 and 3. So we'll choose that particular monomer, and where it is going to react is between reactive point 1 and the reactive point 3. For that we have to assign, since we are just breaking between these, and the reaction condition should be defined between these one particular reactant molecule. So we have chosen both the monomer as similar because we need to break this particular bond here. So since we have assigned the reacting point 1 and next should be 3, so we have given the conditions for the reaction point 1 and 3, and the conditions to be given is here. Either I want to connect this bond, or I want to do the scission or do the chain reactions. Right now we have to cut this bond, make this double bond as a single bond, so that we have the availability to bond with the other monomers, which is the our initiator. So I am going to break this and I'll click save, and as you can see, condition has been applied. Similarly, the next thing is what I am going to do is, now we have broken the bond, is to connect it over here. So for that case, what we can do is we can connect this two reactive point 2 with the this one reactive point 1 of the reactant monomer. So for that case we can choose the first point, which is our initiator, and in the initiator this reactive point 2 is going to be used for the reaction. Since this as we have added this no hydrogen point, that means this place has the occupancy to be bonded with the recently cis bond here. So what we can do is we can use this reactive point to bond with the another monomer of CH2 CHCl of the one atom, and here we are going to connect it. Okay, and here the options which are available for the reactions to take place is the angstrom distance. Like to form a bond or to break a bond, the reaction modeler uses the distance criteria over here. If this threshold distance is less than the specified distance that we have provided to the system, it will bond. If it is more than the specified threshold distance between the two particular reaction points, then it will break. So for this particular case, we are going to assign 5 angstrom as the threshold distance between the reaction to take place between the reactive point of the point 2 and the reactive point of the 1 for the initiator as well as the reactant. Next is the method to be utilized for the reaction. First is the probability conditions, or we can use the Monte Carlo method to do this for the connection or the formation of the bond between the two monomers or the two different uh, initiator, like the different connecting the bond between the initiator as well as the reactant. So for this case we can use the probability function. So I want my reactions to be completed at 100% rate, so I am giving the probability to be 1, which is a maximum, and later the interval of reactions to be 100, and the non-reaction distance between the bond number is 3. We are going to keep other thing as default. As you can see, we broke this bond and then connected with at point 2. So these two corrections that we have provided, and now we can go with the chain reactions to follow. So this was the initial conditions that we had provided. As next is we have to initiate the chain reactions. So for that case we have to use the our our reactor, which is going to be used for the chain reaction. And as you can see, we had three options of connecting, scission, and the chain reactions. So I'm going to choose the chain reactions and I'll click save. And as you can see, we have applied all the conditions which is required for the chain reactions to follow. So till now we first break the bond between the reactive point 1 and 3 of the reactant, which was a double bond. Then we connected this one reactive point of the 2, which had the availability of the bonding with the reactive points of the 1. So here it has bonded, and again as you can see, the reactive point 3 is left open to be bonded again. So again, that's how what we did is we chosen the same monomer again, the reactive point is chosen 3, and then it is going to again react with the initiator of the point 2, because another initiator will be available and will add the number of initiator and the reactant for this particular chain reactions to proceed with. So once we are done with applying the conditions for the chain reactions to follow, we can go with the reactive generation. If we click on the reactive generation, and as you can see, it has connected that particular uh, point of the reaction which we assigned here into the conditions. As you can see in the post reaction tab, here we have seen the reactive point 1 is getting bonded with the reactive point of the 2 of the reactant. Once this is done, then we have to apply the force field to the system. Again, as I mentioned in the preparation of the monomers, we have to follow the same force field. So again, I am going to use the dreading. Once the force field has been applied, we can choose check the charges, extra charges, if it is available on the system, which is not. Once this is done, then we can move ahead with the creation of the input file. And as you can see, the next option is the clear post reaction. If some conditions are not perfectly met and the reaction is not as you wanted, then you can clear it, and again you can go back to the previous step, and then you can change the conditions which is required, and then you can again press to reactive generation, and then it will create all the probable reaction sites which you have assigned in the previous step. and it will form a bond and even break the bond depending upon the conditions which you had applied. So once we have given the conditions for the input pre-reactions and we got our post-reaction conditions available, whatever depending upon our input reaction conditions, then we can create our input file. To create the input file, we have to specify the simulations conditions first, the total number of steps, interval, delta T, the temperature, the pressure, and the algorithms. So right now I am going to keep all these as by default. Next is the boundary conditions. Under the boundary conditions, we can choose the initial density that should be assigned to the input file. I'm going to choose as 0.5 gram per centimeter cube. The next important tab is the polymer tab, where we can choose the number of, okay, let's remove this first. So from here we can choose the number of monomers that we had added here into the reaction modeler. So from here we can choose. So we need initiator to be just 1 and the reactant to be 100. Okay, so this is our initiator, and then we can add the reactant to be 100, where this is how our cross chain reactions should takes place with the help of just one initiator. Once this is done, we are going to leave other tabs as by default, and then as you can see, this is the input file name, chain reaction underscore in .udf, and then we can hit on create, and then it will create an input file for us. And as you can see, the monomers, or you can say the initiator and the reactants, has been registered here into the simulation box. The simulation box parameters, the lattice parameter like the cell size, the angle and the density and the total charge into the system, and the force field which has been applied here are mentioned over here. The first thing that we should be doing is to minimize its energy and optimize its density. For that case, we can choose the simulation conditions. Under the simulation condition settings, and as you can see, these are the same settings which were there while creating the input file. I am going to run this NVT calculations as it is, and then we are going to run the engine. And for the reaction modeler, VSOP is the engine that we have to use for the reactions to take place. And as you can see, this reaction flag is on, but since we are only minimizing energy in this particular step, so we have to turn off the reaction flag and then click on the start VSOP, and it is going to minimize its energy first, and then in the next step we are going to use the reaction flag on in the same tab of the VSOP engine, and we'll wait till this minimization is complete. So once the reaction completes, we can check our output file is been generated, and we can check it. And as you can see, the energy is going to be minimized since we ran this particular simulation only for the 10 picoseconds. So we can choose and see how this is for how long we have to run it. To just showcase, I am just running for 10 picoseconds. We can choose it depending upon for better accuracy we should run this particular minimization step for at least 100 picoseconds. Once this is done, we have to take the last output file since we have the 100 frames, and then we can click on the C edit with the COGNAC modeler, and it is going to take the last output file as an input, and I am going to rename this particular output file as react and click OK, and this is the energy minimized output file from the previous calculations. Again, Since energy is been minimized, now we'll run for the reaction conditions. We are going to use the same simulation conditions, having the total number of step as 1000 10,000, and the delta step as 1 femtosecond, and the output interval as 100, and the normal temperature pressure. We can click on the engines. We are going to choose the VSOP engines. As I mentioned, for the reactions to take place, we should be using the reaction VSOP engine. And now in this particular simulations, we are going to turn on the reactions, because this is the step where our chain reaction is going to take place, and we can choose the maximum subcell number of for the control. So we are going to make it as 100, and we can limit the number of added bonds on the reactions. Okay, so that our reaction completes formally without any problem. So we are going to make it as some 1000 bonds which has been added here. So this is the limitations has been applied here for the bond formations, angle, and the torsion. Once this is done, we can click on the start, and our cross linking, or once we start our engine, we can see that how the chain reactions complete. Once the simulation completes, I'll show you the chain reactions simulation. So our reaction is been started, and as you can see in the log table, this is the log file, and the now our simulation has completed for the reaction. So as you can see, our output file has been generated, and we can click on OK. And to see whether the reaction has taken place or not, we can choose this option to draw target. And as you can see, only two types of the file are available. And as you can see, initially we added the reactant to be 100 and the initiator as a 1. And let's check the reacted sites, or the reacted monomer which has been generated via the chain reaction using the chain reaction modeler. So we are only going to see the mole 122, and as you can see, the reaction has been followed. So this was all. This is how the reaction modeler works for the chain reaction conditions. If you would have ran for this particular simulations for the longer period of time, the more chain reaction would have followed in this particular chain reactions. And to see the how many bonds has been formed, we have one script we can use is the bond form, since as you all know, the Python scripts are able to be run here into the simulations. And as you can see, we are going to print the number of molecules, number of atoms, and the number of bond for all these 100 frames of the simulations starting, and this is going to take the total record, which is 100, and then it is going to calculate. Once you run this Python script, and you will be able to see in the log file, initially we had the number of molecules to be 101, number of atoms 607, and the number of bond as 506. After the simulations, as you can see, the number of molecule has been reduced to 79, and the number of atoms to 607, and the number of bond is 528. And as you can see, it has the number of bond initially was 506, and after the simulation it has 528, means the number of bond has been increased since the chain reaction has been taken place. So this is how this chain reactions tutorial simulates, and whatever the input conditions which were there here we had assigned, Once this is assigned, we can create the input file and then minimize its energy of the input file. Once this is done, we can use the VSOP engines conditions to run this chain reactions to obtain the desired output file. Thank you.